Now here's an equation, or here's an example that we can use for equation 3. So example C says a car traveling at 100 kilometers per hour south accelerates at 3 kilometers per hour squared south for 2 hours. What distance did the car travel? We need to use this equation, equation 3. So delta D, VI delta T plus half a T squared. Substituting in some values, it was moving first at 100 kilometers per hour, 100 kilometers per hour times 2 hours. That's how long it was accelerating for. Plus half times its acceleration, 3 kilometers per hour squared, times 2 hours squared. Okay, so that's going to give us 200 kilometers plus half times 3 is 1.5. 1.5 times 2 squared, which is 4. 1.5 times 4 gives us 6 kilometers. 200 plus 6 gives us 206 kilometers. So there's our answer for example C. Okay, as we were deriving equation 3, we substituted in some values for VF. This time, we're going to do it a little bit differently. We're going to substitute in values for, we substituted for VF for obtaining equation 3. This time, we're going to substitute for VI. So we're needing to rearrange equation 2 for VI. So we're just doing that here. So VI is VF minus A delta T. Substituting the VI into equation 1, we get delta D is VF minus A delta T plus VF. Right? So this was from equation 2, and this is all basically equation 1. Adding the VFs together, we get 2VF minus A delta T over 2 times a delta T here. Okay, the 2's cancel each other out, and the final form that we get is displacement is equal to final velocity times delta T minus half A T squared, or half A delta T squared. So there's our equation 4. Now this makes sense in terms of the graph too, because what we've basically done is we've taken VF delta T. Well, here's VF here. This is the level of VF, and here's our delta T. So we found the total area of this great big rectangle, and then we've subtracted something. We've subtracted half AT squared. Well, the base, delta T, multiplied by half, multiplied by this height, which is acceleration times delta T, is going to give us the area of what's above the curve here. And so in order to find the area under the curve, we've basically taken this big chunk of area and subtracted away this small triangle in order to find the full answer. Okay, so that's equation 4. Here's our example for equation 4. A mouse runs and accelerates for 5 seconds at 2 meters per second squared west and reaches a velocity of 13 meters per second west. What distance did the mouse cover in this time? There's our equation 4. So final velocity times delta T minus half A delta T squared. So the mouse had an initial or a final velocity of 13 meters per second, and he was accelerating for 5 seconds, running across the floor. And so we subtract half times the acceleration, 2 meters per second squared, times delta T, 5 seconds squared. Okay, 13 times 5 gives us 65. Half of 2 is 1. 1 times 5 squared is 25. And so the displacement of the mouse, the change in position of the mouse, is a total of 40 meters west. Here is our equation 2 again in all its glory. Vf is equal to Vi plus acceleration times the change in time. Okay, if we play with that a little bit and square both sides, okay, then we're going to end up with Vf squared equal to, now if we square this, we're going to have to multiply all of this by itself, so we'll end up with Vi squared plus 2 times Vi times a delta t here, okay, plus a squared delta t squared. Okay, and rearranging that product a little bit, we've got our Vi squared. If we factor out 2 times acceleration, take that out of the first term, we get Vi delta t. If we take it out of the second term, there was no 2 to cancel, so we'll end up with a half. We've still got 1 acceleration left over because it was a squared, and we're left with our delta t squared. And this, all of this, according to our equation 3, which we derived before, is the same as displacement. Vi delta t plus half a t squared is change in displacement. So our equation can now be Vf squared is equal to Vi squared plus 2a delta d. And that's our equation number 5. Okay, final question of the lesson. A horse arrives at a field. We're going to be using equation 5 here. A horse arrives at a field and it's moving at 9 meters per second west. And then it accelerates across the field at 0.25 meters per second squared west. If the field is 30 meters across, what is her velocity when she reaches the other side? Okay, there is equation 5. Vf squared is equal to Vi squared plus 2ad. So, initial velocity of 9 meters per second is squared plus 2 times 0.25 meters per second squared times 30 meters for the change in position. Okay, so we have 9 squared is 81 meters squared per second squared. We have to square the units as well. 2 times 0.25 meters per second squared times 30 meters gives us 15 meters squared per second squared. So we add those two together, we end up with 96 meters squared per second squared. But we're trying to find final velocity, so we take the square root of both sides. So Vf is equal to square root of 96, which works out to be 9.798 meters per second.